Okay, so in this part of the lecture, we're going to be looking at simultaneous equations. So simultaneous equations are really quite important because they help us find where lines bisect. So for example, if we take the plot y equals 2x, maybe y equals minus 2x plus 5, and we were just to kind of give an idea how they were drawn. So this would be 1 crossing through 0, 1 crossing through 5, and we have a y-axis and an x-axis. We want to find out where these 2 points cross. So this could be a surveying point, this could be something that you're looking at in your studies. So if we wanted to find the coordinates of x and y, we could sub these two into each other, or we could do simultaneous equations to help us do this. So what we can do is if we just reorganize these equations a little bit to say y minus 2x equals 0 and y plus 2x equals 5, we could subtract these two answers from each other to get the y's to disappear. So we have minus 4x equals minus 5, and we could then say that x equals 5 over 4, which equals 1.25. If we then sub that back into our initial equation where we said that y minus 2x equals 0, well, we also know from there earlier that y equals 2x. Therefore, y equals 2 times 1.25, which equals 2.5. So if we go to our graphing software and we look at our two lines of y equals 2x and y equals minus 2x plus 5, we can see on the y-axis they cross quite nicely at 2.5, and on the x-axis they cross quite nicely. We follow this one at 1.25. That is our answer, 1.25. So that's just a simple method of looking at this, but perhaps we want to look at something slightly more difficult. Perhaps we have something using 3 coordinates in 3 dimensions. So what happens if we have the equations x plus y minus z equals 4 and 2x plus z equals 7 and 3x minus 2y equals 5. So we can call these equations 1, equations 2, and equations 3. So what we can do is start by looking at things that look similar. So what I can see here is we can get rid of z perhaps by adding equations 1 and 2. So let's do that. So we say x plus y minus z equals 4, and we add, and we add 2x plus z equals 7, we can say that 3x plus y equals 11. So we've now made another equation. Perhaps we could call this equation 4. So now we have this, we can perhaps sub this into a different equation. So say we look at now equation 3, what we can say is, well, we have 3x plus y equals 11 from equation 4. And equation 3, we have 3x minus 2y equals 5. So if we were to subtract these two from each other, we'd actually get a solution for y. So we could say that 3 minus 3 is 0, 1 minus minus 2 is 1 minus 2 is 3y, and 11 take away 5 equals 6. Therefore, we can find out that y equals 2. So now we've got this. This is where we begin plain sailing. Is we have an answer for y, so that means that we can then start to solve x. That becomes quite simple. So we take this initial equation of equation 3, and we can say that 3x minus 2y equals 5. So we could say that 3x minus 2y equals 5. So we now know a value for y, a value for x as 2. So we can say that 3x minus 4 equals 5. So therefore 3x equals 4 plus 5, or 5 plus 4, so x equals 3. So we've now got two solutions to our problem. So if we just go back to the top and we can see what we've got x equals 3 and y equals 2. So we can now work out z. So let's take the original equation, equation 1, and we say x plus y minus z equals 4, and we take our x, which is 3, plus our y, which is 2, minus z equals 4. So we can then say minus z equals 4 minus 3 minus 2, which equals minus 1, minus z equals minus 1. Therefore, if we work out, we just change our negative signs, we can say that z equals 1. So we have our answers of z equals 1, y equals 2, and x equals 3. So we can actually check this in one of our equations, or all of the equations from the top one maybe. We've used that already, so we can say, so 2x, so 2 times by, in this one, 2 times by 3, plus z plus 1, which would be 6 plus 1 equals 7. And maybe we can check it here with the x. 3 times 3 is 9, minus 2 times 2, which is 4, equals 5, and we know we've got the correct solution to our answer. So those will be the solution to the problem, and that would actually mean in 3D space, if we go onto the plotter again and we think in more of a 3D world, the point at where these three planes connect is the point of intersection here, and from these you can find out where all the points in x, y, and z locations are located. Okay, so let's try another problem. What have we got? So this is maybe a slightly more tricky problem where we have something like x minus y plus 2z equals 6, 2x plus y plus z equals 3, 3x minus y plus z equals 6. Okay, so we're going to call these equations 1, 2, and 3 again. Okay, so what can we do? So if we add equations 1 and 2, that's going to get rid of our y. So let's do that. So 3 minus y plus 2z equals 6, and we can then say 2x plus y plus z equals 3. So we add these together, and we're going to cancel those two out. There's going to be an add sign here. And so that's 3x plus 3z equals 9. Okay, so this is our equation 4 now. Okay, so now we've got an equation 4. If we need to do something else. So we need to, again, try and get rid of another value. So we have an x and a z. Maybe if we were to now add equations 2 and 3, we would get rid of this y here. So if we said 2x plus y plus z equals 3, and we have 3x minus y plus z equals 6, okay, and we add these together, that's going to help us get rid of this y, which means that we have 5x, 5x plus 2z equals 9. So now we have a second equation, a fifth equation. So we're actually making this more complicated, but we're reducing the terms as we go along. So now we have, if we have equations 3 and 5 with similar terms, perhaps we can say 3x plus 3z equals 9, and we have 5x plus 2z equals 9 also. But we want to find some like terms. So a bit like our fractions, we want to find things that add up. So perhaps if we were to multiply the top by 2 and multiply the bottom by 3, that would then give us 6 in the z's, which means we could subtract them, and then we would get a decent value then we can get a value for x. So let's do that. So that would be 3 times 2, which is 6x, plus 3 times by 2, which is 6z, equals 18, which is 9 times by 2. We have our subtract ready and raring to go. We could have 15x on the bottom. We could have 3, so that's 3 times by 2 plus 6z, so that's what we're going to get rid of, equals 27. So we say that 6 minus 15 is minus 9. We've got rid of these two here, and we have that 9x, and we have that 18 minus 27 would give us 9. Therefore, x would have to equal, or minus x would equal 1, and x would equal minus 1. So that is our first x would equal, would be minus 9. Oh, sorry, 18 minus 27 is minus 9. So we have minus x, and that would be minus 1. So our first solution to our problem is x equals positive 1. Okay, so we can put this back up here, x equals 1. So we now need to go on a second hunt. So what can we do here? So perhaps we now know the example, we now know the answer to this. So we know that x equals 1. So if we were to sub in two equations, maybe 1 and 2, we could then solve quite easily for z because we already know x. So we take the first equation from the top, which is x minus y plus 2z equals 6, and we can say that 2x minus plus y plus z equals 3. We now know what x is, so we can say that is 1 minus y plus 2z equals 6. And we can say that 2 times 1 is 2 minus or plus y plus z equals 6. So now we have another subtraction which we can do here. Oh, equals 3, sorry. So we have another subtraction which we can do here. We can say 1 minus 2, which is minus 1, minus, if we add the two together, we'll get rid of the other y's. So 1 plus 2 equals 3, minus y plus that is we've got rid of this. 2z plus 3 is 3z equals 6 plus 3, which is 9, equals 9. So we have our term over here. So we can now say if we have 3z equals 9 minus 3, so therefore 3z equals 6 and z equals 2. So we now have two solutions to our problem. We can then go back because we know z equals 2, and we can put this into any of the equations to help us find it. Perhaps we take equation 1 because that looks like there's the least amount of terms. So we can say from equation 1 that x minus y plus 2z equals 6. So we know that x we've worked out here as 1. That was our answer here, 1. Oops. And we have z as 2. So we can say that 1 minus y plus 2 times 2 equals 6. So then we can begin to tidy this up a little bit. So we find our value for y, which would mean that minus y equals 6 minus 4 minus 1. So minus y equals 5. Therefore, y equals minus 1. So we now have the solutions to our problem. All the way to the top, y equals minus 1, and this can be checked. So if we check it in equation 1, we could say 1 minus y minus 1. So that's 2 plus 2 times 2, which is 4. So plus there, so 2 plus 4 equals 6. And we've got the right answer to our question. Okay, so what happens if we want to extend this a little bit and we want to look at what happens if we have a quadratic, maybe something that looks a little bit like this. We want to find out where the line crosses through here. So maybe we have two solutions where the line crosses. So if we take an example such as x minus y equals 2 as our first equation, and we have something like 2x squared minus y, 3y squared equals 15 as our second equation, we can begin to work out where these lines will cross. But we have to do this in a slightly different way because we need to do a little bit of rearrangement. So what happens if we work out in terms of x what things are? So if we look at equation 1, we can say that x now equals, if we're a bit of a rearrangement, we can say that x equals y plus 2. Okay, so that's quite nice and tidy. And we have on the bottom 2x squared minus 3y equals 15. So with this x value, we know this, so we could substitute this in. That's y squared. We can substitute this in. So we say that 2y plus 2 squared minus 3y squared equals 15. Okay, so a little bit of expansion of brackets and a bit of fun here. We can say that 2y, so we're going to expand our brackets, that'll be y squared plus 4y plus 4, our brackets are here, minus 3y squared equals 15. Okay, so again, we can tidy this up a little bit further. We can say that we have 2y squared plus 4y, oops, 8y plus 8 minus 3y squared equals 15. So 2 minus 3, 2 plus minus 3 is minus y squared, minus 5 squared plus 8y. We have a 15 on this side, so 15, we bring it over to this side. That'll be a minus 15 plus 8, which would give, minus 15 plus 8 gives us a positive 7. We minus it onto this side. It gives us a positive 7, negative 7, sorry, negative 7, and that equals 0. We have a negative term here, so we can multiply all the way through by minus 1. So we now have y squared minus 8y plus 7 equals 0. And wow, we've got a quadratic here, with our favourites, that we can now solve quite simply. We could do this with the quadratic rule, but we can see that this is quite a simple quadratic to solve. So we have a positive and a negative. That means that both sides have to be negative. We need two values that, when added together, need to equal 8, and two values when multiplied together equal 7. So that would have to be 1 and 7. So this means we now have two values for y. We could say that y equals minus plus 1, or y equals plus 7. Therefore, we now have two values for x as well. So if we go back to the original simple equation of x minus y equals 2, we can write that just here. X minus y equals 2, we can find that x equals 2 plus y. So we just add 2 onto these values, which makes it quite simple. So we can say that we have x equals 2 plus y. So we have two values of either 3, where x equals 3, or x equals 9. Okay, so that's our two solutions to the problem. So if in the exam, I would want to have an answer that looks a little bit like this, because there are two solutions to the problem. You think if we have something crossing, the quadratic is crossing a linear equation, which is going to look something like that, it's going to cross at 2 points. And these are our two solutions to our problem. Okay, so next we're going to move on to our next problem, which is we're going to be looking at logarithms. So that was simultaneous equations. We're going to move on slightly into logarithms. It's going to be the last part of this lecture today, and we'll just touch on it later before we don't pick it up into the